Alright, so today's topic is going to be falling objects and gravity. And to help us, we've got some high-tech demonstration apparatus here. Different things at different weights. So let's say I pick up a couple of different objects, say a tennis ball and a softball, and I hold them up at a certain height and I drop them. Which one's going to hit the ground first? Now, give you a chance to think about it. You may think you know the answer to this one. So, I know some possible choices. Are they both going to hit the ground at the same time? Is the heavier one going to hit the ground first? Is it going to be the smaller one that hits the ground first? Is there any way to tell? So have a little think about that, and let's just do the experiment. This is an experiment you can do at home. I'm just going to hold them up at about the same height, drop them, and they're going to hit the table, and you're going to be able to see and hear whether or not they hit the ground at the same time. So 1, 2, 3. They both hit the ground about the same time. Now you may be thinking, well, that's not too surprising. These things both weigh about the same amount. Well, what if we tried some things that are very, very different masses, very, very different weights? Let's try, for example, a tennis ball that I filled with steel ball bearings, right? So it's really heavy. Hold up to the camera so you can hear the sound. This was just a regular tennis ball, right? So I have different weights. One's much heavier than the other. This one weighs about a pound. This one just weighs a few ounces. So let's try that experiment now. Right, it's a good scientific experiment. They're both the same size, but they're different mass, different weights. I'm going to drop them. 3, 2, 1. And again, they hit the ground about the same time. And you drop them about 1.5 meters, but still. Let's do it again. Same rate, both hit the ground about the same time. Now, what? I hear you wondering if I had picked some things that were a really big difference in weight. Because many people, probably some of you watching this, are still thinking, well, heavy objects hit the ground first. Everybody knows that. So let's try something. Let's try a really big difference in weight. So I've got here a 1 kilogram weight. I can hold it up to the camera. I don't know if you'll be able to see that. It weighs a kilogram. It's heavy. I've got here little tiny 10-gram weight. So these differ in weight by, well, 1,000 grams, 10 grams, so this is 100 times heavier than this one. I do the same experiment again. I'm going to hold them up. Whoa. So we've got a 1 kilogram weight and a 10 gram weight, right? 100 times heavier. So we're going to hold them up. Is there any difference in how fast things fall, depending on how massive they are? We should see it, because there's a factor of 100 here. So let's do it very carefully. 3, 2, 1. Alright, they hit the ground exactly the same time. They fall at exactly the same rate. And, you know, that may be surprising to some of you. A factor of 100 times difference. If there were any difference, you would have seen it. Now, probably some of you are thinking, well, hang on a minute. What about air resistance? What you've just said is only true on the moon. Am I on the moon? This isn't the moon. This is the University of Massachusetts, Lowell, where the air is just the same as where you live. So, air resistance didn't matter. So when does air resistance matter? When doesn't it matter? You know, we can repeat the experiment. Even with little tiny things, a little tiny plastic bead here. I can drop my little tiny plastic bead at the same time as my, heavy-weighted tennis ball. They still hit the ground at the same time. So apparently, everyday ordinary objects all fall at about the same rate. We're talking about the same amount of time to fall a certain distance. Now, let's try some other objects, because you're thinking, well, that's not true. I bet if he drops a feather or a piece of paper, I bet that won't fall at the same rate. Well, let's just try that. Here's a big old textbook. Let's take my textbook, and just for the sake of argument, we'll use our tennis ball again. So I'm going to drop a textbook on a tennis ball. Okay, about the same. What else can we try? Oh, I know. How about, let's see if a piece of paper falls at the same rate as a big heavy textbook. What do you think? What do you think's going to happen when I take this piece of paper, drop it, same time as the textbook? Well, let's find out. Okay, this is an experiment after all. Now, you may be thinking, oh, there was some kind of aerodynamic effect. The paper was stuck to the book. Well, the paper isn't stuck to the book. just rest it on the top. So, paper. Even a piece of paper falls at the same rate as a hardback book, falls at the same rate as a kilogram weight, falls at the same rate as a tennis ball. Doesn't make any difference. Let's try something else. How about a feather? Alright, here's a feather. Very fluffy feather. Now, for those of you who are thinking, well, maybe that paper is stuck to the book somehow. Yeah, the feather is not stuck to the book. I'm just going to rest it on the book, bring it up close. There's no cheating here. There's no magic trick, okay? There's no glue, no stickies, just a feather. Okay, we'll walk back. Let's do the experiment again. Do the table. Hold it up. Drop it. How about that now, huh? Let's try it again. I'm going to drop it all the way from the roof to the floor this time. I think that's a pretty good demonstration. Feather hits the ground at the same time as the book. Now, maybe some of you again thinking, ooh, there's some woo-woo aerodynamics. That feather was somehow stuck to the book by air currents, okay, that were coming around the book. Well, let's see if that's true. Let's take the feather, put it on the book. Look, plastic Tupperware container, put it on the top. Now, if the feather really falls slower than the book, then as this whole thing falls together, the feather should get stuck to the top, the inner side of the lid, right? See what I'm saying? If the book is falling very rapidly and the feather's falling slowly, they ought to separate apart in the air as they fall. And if that happens, then the feather ought to get stuck on the inside top of the lid as they're in the air, which we'll be able to see by slowing down the video when we play it back. So let's try that as an experiment. All right, book, feather, Tupperware, pick it up to a great height, and watch very carefully, it's going to be hard to see. Now, apart from the fact it fell off at the end, I bet when we slow that down and play it back, you will see that feather just falling like a stone on top of the book. Let's try one more time. So, all objects fall at the same rate. Now, what is that? Who discovered that? Famously, in the history of science, Galileo of Italy, Pisa, famously discovered that, wrote about it, and it was a very surprising discovery for people. And now you've seen it too, and you can go and do that experiment for yourself at home. Yeah, you still think I'm cheating, don't you? So let's write up the equations to see if it makes sense, right? Gravity, according to Isaac Newton, force of gravity, the weight of an object, W, the weight of an object, equals the mass of the object, m, times g, which is this mysterious acceleration due to gravity. Okay? This is actually just a special case of Newton's second law. Which says that in general, any force is equal to the mass of the object times the acceleration it is subjected to. So if we want to know what's the acceleration that any falling object is subjected to, we can rearrange this equation. Say, well, if F equals ma, the acceleration that the object feels in response to a certain force is just going to be that force divided by the mass of the object. If we're talking about the weight of an object, that force is mg. Now, right, but A, the acceleration due to gravity in this case, is going to be the weight of the object, mg, divided by the mass of the object, m. M divided by m is 1, so they cancel out. What that means is that the acceleration of a falling object due to gravity always equal to this mysterious thing g. You might wonder what that is. Well, that turns out to be the strength of the local gravitational field. So, write one more equation. I'm not going to write lots of equations. G is the gravitational constant, which is just how strong is gravity, times the mass of the thing doing the gravitating, which is the mass of the Earth in this case, divided by the distance between the center of the Earth and the object that we're talking about. Let's call that r. Squared. So that's what g is, the acceleration due to gravity. It's the same for every object that we might pick up. It doesn't depend in any way on the thing that we're holding. So all objects fall at the same rate. And your physics teacher, if you ever had one, might have said, well, in the absence of air resistance. But I think our little demonstration there showed that, most of the time air resistance doesn't matter very much. So you don't need to go to the moon to do this experiment. I'm just going to do it again because I love seeing it. You don't need to go to the moon to see a feather falling just like a stone. You can just do it right here. And that's all for today.